2,500 degrees Fahrenheit. That's the cold end of the range. On the hot end, it climbs past 3,000. Hot enough to turn scrap steel into standing liquid. Hot enough that the men who worked beside it timed their whole shift around how many minutes they could stand 2 yards from an open door and still walk home afterward. Now put a machine in front of that door. 60, 80, in the biggest shops closer to 100 tons of moving steel, crawling on rails the width of a city street, carrying an arm long enough to reach straight into the fire and turn a half-ton box of scrap upside down without a man ever laying a hand on it. That was the promise. Keep the men back. Let the machine take the heat instead of their skin. It didn't keep that promise. What went wrong? It carried a man's seat right up against that same open door, close enough to watch the flame breathe, close enough that when the furnace pushed back, and it did, on more than one floor, in more than one decade, there was nowhere in that cab to go. This machine has a body count, not from what it built, from where it put a man to build it. For 60 years it fed the furnaces that fed a nation, rails, warships, bridge steel, the beams inside towers you have stood under without knowing it. Steel made in furnaces exactly like the ones it charged went into the frame of the Empire State Building and into the hulls of the ships that crossed the Atlantic during the Second World War. Almost anything built out of American steel before 1980 owes something to a machine like this one. Then, in less time than it takes to eat lunch, a smaller, uglier, faster machine did its whole job better, and every one of these things went quiet, one furnace line at a time, until floors that used to shake under their weight went still enough to hear your own boots. This is the furnace charging machine. This is how it helped feed an empire. This is how it turned on the men who ran it. And this is how, floor by floor, it was hunted down and taken apart by something a fraction of its size. Chapter 1. The machine that fed a nation and turned on the men who fed it. Here is what this machine could do, and here is what it did to the men who ran it, before you hear one word about how it worked. It moved on rails laid into the furnace floor itself, hauling tons of steel scrap in a single pass, threading a box the size of a coffin through an opening barely wider than a doorway, into a chamber hot enough to boil water 40 feet away. That part is almost boring. Machines move things. Fine. Here is the part that isn't boring. Feed that furnace wrong, or open its door at the wrong second, and it didn't just resist, it answered. Pressure inside a furnace running that hot doesn't sit still, it swings. And when a door opens into a swing it shouldn't, flame comes back out through the same opening it just went in through, straight at whoever is sitting closest. Steel men have a word for it, flareback. It's not folklore, it's a documented, named hazard, with its own line in the safety manuals, common enough that mills eventually bolted heat shields onto machines that were never built with any. So why would a machine need a shield bolted on years after it was already standard equipment in every mill in the country? The answer is the same reason the furnace doors themselves were built with water running through their steel frames, just so they wouldn't warp from standing that close to the fire. The door got cooling. The man running the charging machine, in the years before somebody finally added a shield, got a windshield if he was lucky, and open air if he wasn't. Here's a number to sit with. In 1948, on a furnace floor built to the same standard as every charging machine's territory in the country, 3 men working the open hearth at a Midwestern steel plant were caught when the furnace answered back, hot metal erupting across the floor in a single violent second. One of them died 18 hours later. He'd been burned over 90% of his body. 2 more died beside him. A 4th survived and never worked in a mill again. That is not a rare footnote from a dangerous industry in general. That is what this specific machine's floor did, on a day like any other, to men standing exactly where this machine's operator stood, every single shift. A big open-hearth shop didn't run one furnace. It ran a dozen, sometimes more, lined up door to door down a single building, and one charging machine's rail line could serve every furnace on that row. At full production, that meant this machine, or one just like it, was almost never actually still. It was always rolling toward one door, or pulling back from another, somewhere on that line. For every minute of every shift, the shop was running steel. How many machines like this one are still charging a furnace in America today? None. We'll get to why, and it's a worse story than you're expecting. Not a story about a machine getting old and tired, but a story about a machine getting humiliated by something a fraction of its size. Every accomplishment this machine can claim came paired with a bill nobody in the front office had to pay personally. It also burned men on floors just like the one it stood on, in a job built specifically to keep that from happening. Here's the part that should make you angry before we've even started. This machine was invented to stop exactly that. A man standing at an open furnace, unprotected, taking a fire to the face. And then it put a man at an open furnace, unprotected, taking a fire to the face. We'll come back to that. It's the reason this video exists. The reason a machine built specifically to pull men out of the flame ended up parking one of them in the seat closest to it. And we'll come back to how something engineered to run for 100 years disappeared from this country almost overnight, replaced by a squat little vessel that could finish its whole day's work before most men finish their coffee. 2 debts. Keep them both open. We're paying them off, one at a time, starting now. Chapter 2. Built to pull men out of the fire. Before there was a machine to do this job, there were men with iron rakes, standing at an open furnace door, feeding it by hand. That sentence sounds almost quaint until you sit with it. A furnace running at close to 3,000 degrees doesn't care how strong you are. Before mechanized charging, crews shoveled and pushed scrap and pig iron through the furnace opening with long-handled peels, close enough to the flame that a full shift left a man's face raw and his lungs full of whatever the fire was throwing off. One steel worker who lived it, a helper on the 12-hour turn at an open-hearth shop, kept a diary of what the job actually did to a body. He described stepping on a stone one evening and only then noticing the spot on his heel where sweat and mineral dust had quietly worked themselves into a burn over the course of the day. An injury so small it hadn't even registered while it was happening. That was a normal Tuesday on this floor, not a bad one. How do you feed a furnace holding more steel than a freight car can carry, fast enough to keep it running, without killing the crew that has to do it by hand? For decades, nobody had a real answer. You just used more men, in shorter bursts, and accepted the toll. The man who finally solved it had already spent 2 decades inside this exact danger. Samuel Wellman was an engineer who, in 1870, built the first commercially successful open-hearth furnace in the United States, at the Bay State Iron Works in Boston, the very furnace type this entire story runs on. He went on to run construction at the Otis Iron and Steel Company in Cleveland, a mill that grew fast enough under his watch to help make its owner one of the most dynamic small steel producers in the country. But Wellman kept circling back to the same unsolved problem. How do you feed that furnace without feeding a man into it? By 1896, he'd founded his own engineering firm in Cleveland with his brother and a partner, specifically to build the answer. The answer was a machine that could reach into the fire on a man's behalf, so nobody else had to. It worked, and it worked fast. Charging that used to require a full crew with hand tools could now be handled by one operator moving a half-ton box at a time. Furnace shops that used to be capped by how much scrap a crew of men could physically move in an hour suddenly weren't capped at all. Steelmakers who had kept their furnaces small because human muscle was the bottleneck now built furnaces holding 60 tons, 100 tons, eventually up to 600, and every ton of extra capacity meant a longer shift, standing beside a bigger fire for the one man left in the room with it. Charles Schwab, who ran Bethlehem Steel and had personally watched every major advance the industry produced, said Wellman had done more for the development of steel than any other living person. Schwab didn't have to stand in the cab. That's an easy compliment to hand out from an office. Cleveland's steel mills were already running thousands of men through their gates by the time Wellman's machine started appearing on their floors. The Cleveland rolling mill alone employed more than 8,000 at the height of its independence in the 1890s, and every one of those furnace floors had, until then, depended on brute manpower to keep the charge coming. A machine that could do the work of a dozen men with one operator wasn't just a convenience to a mill running at that scale. It was also a decision about which of those men got to step back from the fire, and which one didn't. By 1903, the company had grown enough to bring in a third partner and rename itself Wellman Seaver Morgan, big enough by then to acquire an entire mining equipment manufacturer just to keep up with demand. Wellman himself didn't stop at the charging machine either. He helped develop the giant lifting magnets that let cranes grab tons of scrap steel in one bite, and an unloading machine that could empty an entire iron ore freighter in hours instead of days. Nearly all of it aimed at the same target: get a human body further away from something that could kill it. Nearly all of it, sooner or later, still needed one man close enough to run it. Here's the debt from Chapter 1, paid. This machine was not built as a monster. It was built as the opposite, as the thing that would finally let a man step back from the fire he used to have to lean into with a hand tool. For the first time, feeding a furnace didn't require standing directly in front of an open door with nothing between your body and the flame but a long stick. Except it did. That's the part nobody fixed for decades. The machine reached into the fire so a crew of men didn't have to, but it still needed one man, sitting in a cab, driving that arm forward every single cycle, his own body now the closest thing to the door. Wellman had pulled a crew back from the flame and replaced it with a single operator sitting exactly where the fire could still find him. We're not done with that furnace door. It's going to come up again. And next time you'll understand exactly why it was so dangerous to stand near. Chapter 3. Half a ton at a time, through a door that could breathe fire back. A charging machine's whole job lived inside one repeated motion, and understanding that motion is the only way to understand why the danger never went away. Picture a long carriage, built like a bridge on wheels, running on a rail track laid parallel to a row of furnace doors, sometimes a dozen furnaces in a single shop, all facing the same line, all fed by the same machine sliding back and forth between them. On top of that carriage sat a second trolley that moved crosswise, and on the front of that trolley, an arm, sometimes called a peel. The arm's job was simple to describe and brutal to execute. Pick up a steel box loaded with scrap, hauled to the machine on a small rail buggy from the scrapyard, drive that box straight through one of the furnace's doors, tip it, and dump its contents onto the hearth floor inside. Then pull back. Then do it again. And again, sometimes dozens of times, until that one furnace held its full charge. Each of those doors, usually somewhere between 3 and 7 of them lining the front of a single furnace, did more than charging. Crews used them to add flux and alloying agents mid-heat, to run off slag, to pull test samples, to make quick repairs to the hearth refractory when it started to fail. Every one of those functions meant another moment when a door had to open onto that fire. And every one of those doors had to be built with cooling pipes running through the steel frame, because standing that close to the flame for hours at a stretch would otherwise warp them out of shape. Sit with what that tells you. The door itself needed active water cooling, just to survive proximity to its own fire. The man sitting a few feet back in the charging machine's cab got no equivalent protection for years after the machine was already standard equipment in every major mill in the country. Why did the furnace need to run that hot in the first place? Ordinary fuel and ordinary furnaces simply couldn't melt steel fast enough or clean enough for mass production. That was the whole reason the open hearth had to exist. It solved the heat problem with a trick called regeneration. Banks of fire-brick honeycomb, stacked in chambers below the hearth, captured heat pouring out of the furnace's own exhaust and used it to preheat incoming air and gas before they ever reached a flame. Cold air went in one end of those brick chambers. Air already screaming hot came out the other, ready to push combustion past 2,500 degrees the instant it met fuel. It was, for its era, one of the cleverest tricks in industrial chemistry. It was also the reason the fire this machine served was never gentle and never predictable in the way a stovetop is predictable. You cannot regenerate your way to a mild flame. And here is where the mechanism and the danger stop being two separate stories and become one. Every time that arm drove forward to dump a box, a door had to open. An open furnace door is a pressure imbalance waiting to correct itself. Hot combustion gas inside, cooler air outside, and a sudden gap between them. Most of the time it corrected quietly. Sometimes, if timing was off, if a valve stuck, if gas had pooled somewhere it shouldn't have, it corrected violently, and the correction traveled outward through the same opening the arm had just used, toward the cab sitting directly in its path. The machine wasn't malfunctioning when that happened. It was doing exactly what an open-hearth furnace does when you crack its seal at the wrong instant. The operator's whole job required him to crack that seal, over and over, all shift long. A furnace like this held anywhere from 10 tons of steel to as much as 600, and the biggest ones stretched close to 50 feet long and 16 feet wide across the hearth, roughly the footprint of a small house, filled edge to edge with liquid metal at a full, violent boil. Feeding something that size wasn't a job you finished in an afternoon. A single heat, start to tap, could run 8 hours, sometimes 12. There was an older, faster way to make steel by the time this machine came along. The Bessemer converter, which could turn a batch in 10 minutes by blasting air straight through molten iron. 10 minutes sounds like it should have won. It didn't, not for the steel this machine helped build. Bessemer steel came out fast and cheap, but a rail-grade batch and a bridge-grade batch could get mixed up in the rush, and the process gave a melter almost no chance to test or correct the metal mid-heat. The open hearth's slow, grinding 8 to 12-hour pace was, perversely, its whole advantage. Plenty of time to sample the bath, adjust it, and know exactly what you were pouring before you poured it. A typical charge ran close to even parts scrap and pig iron, though some mills, without their own source of molten iron, charged almost entirely on cold scrap instead. Slow and correctable beat fast and reckless. For decades, whenever the steel itself needed to be trusted with a man's life on the other end of it. A bridge, a gun barrel, a ship's hull plate. Hold that number. 8 hours, sometimes 12, to run one heat of steel through one open hearth furnace, with a charging machine rolling back to the doors again and again for most of it. Later in this story, that number is going to sound almost unbelievable. Not because it's wrong, but because of what eventually replaced it. Chapter 4. The Seat with No Door Out. You are in the cab. It's the middle of a summer turn, and the furnace in front of you has been running for 6 hours already. Its refractory brick soaked through with heat that radiates even when the door is shut. You throttle the carriage forward on its rails. The trolley slides out. The arm extends, carrying a half-ton box of scrap toward a door that's about to open onto a chamber, running past 2,500 degrees. You've done this motion 400 times this month. You'll do it again in 90 seconds. There's no windshield worth the name on the machine you're driving tonight. That upgrade is still years away at this mill, and there's nowhere behind you to retreat to if the door answers wrong. The rail runs one direction, the fire is the other. That's not a dramatization built to scare you. That's a description of the job, told from the seat where a real man sat for a real 12-hour shift, thousands of times, at furnace shops across this country for the better part of a century. Who else was on that floor with him? The men who worked this shop weren't reckless, and they weren't careless. They were skilled, a melter running the chemistry of the heat, first and second helpers handling the doors, and, eventually, the tap, the charging machine operator running the arm, each with a job that had to fit into the others in the right order or the whole heat could be ruined, or worse. It was the second helper's job, on most crews, to open the tap hole when a heat was finished and molten steel needed to leave the furnace, a job that put a man just as close to the fire from a different angle. Remember that role. It matters later. None of these jobs came with much room for a bad day. A crew that lost the rhythm of a heat could scorch a batch worth more than most of them earned in a year, and a crew that lost its footing near an open door could lose a lot more than money. So the floor policed itself, the way dangerous work always does. Older hands teaching younger ones exactly how far to lean and exactly when to step back. Not because a manual told them to, but because the men who hadn't learned it fast enough weren't standing there to teach anyone anything. The fire wasn't the only thing eating at a man on this floor either. Every charge kicked up a cloud of dust and gas off the scrap and the flux, grit that coated a man's throat by the end of a shift, fumes that had nowhere to go but up past his face on the way out the stack. Add in a furnace roar that ran for 12 hours without a break, and by the time a charging machine operator retired, if he made it that far, his hearing and his lungs had usually paid their own separate toll, quieter than a burn and just as permanent, just slower to collect. In November of 1941, a government photographer working the propaganda circuit ahead of America's entry into the war stopped at a Republic steel plant in Youngstown, Ohio, and caught a shift of open-hearth men resting while their furnace was being charged. The caption written on that photograph at the time reads, in full, "Open-hearth furnace men deserve the rest given them while the furnace is being charged. Not deserve a raise, not deserve recognition, deserve a rest." That's how plainly the danger and the exhaustion of this floor were understood by the people watching from outside the fence line, let alone the men living it from the inside. The danger didn't retire when the open hearth eventually did, either. It just moved to newer furnaces, which tells you something about how deep this hazard runs in the whole trade, not just this one machine. Decades after the last open hearth in America went cold, a safety chairman for the Steelworkers Union at a mill in Indiana was clearing jammed scrap out of an electric furnace with a forklift in 2019 when hidden material behind the load triggered an instant chemical reaction. He described the moment years later, plainly. A wall of light past 2,900 degrees, then a jet of flame blasting straight out of the furnace opening, engulfing him before he understood what was happening. There was no windshield on the forklift that day, and no face shield on him either. He jumped clear, checked his own body for slag, and only afterward realized he was burned across his ears, his neck, his hands, his legs. He was out of work for 3 months. The mill installed viewing windows and issued head and neck protection at that furnace, only after his body paid the tuition for the upgrade. Different decade, different furnace, same fire, finding the same gap in the same kind of protection. Was that gap ever going to close on its own? No. It closed the way almost every safety improvement in this industry closed, after somebody's skin proved the danger was real. That's the quiet hour on this floor, the 10 minutes between charges when the noise drops and a man can hear his own dinner bucket rattling on its hook, the fire humming low instead of roaring, everyone pretending for a moment that the next 90 seconds will be as calm as this one. It rarely lasted. The furnace didn't keep quiet hours. It kept its own schedule, and the men worked around it, not the other way around. We haven't paid off the titular debt yet. We're about to, and it happened on a floor exactly like the one you've just spent 4 chapters standing on. Chapter 5. The afternoon. The floor answered back. 1948. Indiana Harbor, on the Lake Michigan shoreline east of Chicago, inside Inland Steel's open hearth shop. A floor laid out exactly like the ones this machine ran on in every mill in the country. Rows of furnaces down a line, charging machines on rails in front of them, crews working in the gaps between. A reline crew was on number 1 open hearth furnace that day, doing the punishing maintenance work of rebuilding a furnace's refractory lining while it was down for repair. As they worked the tapping side, something in the furnace let go. Hot steel, already molten, erupted out across the floor in one violent second, splashing over men who had nothing between their skin and several thousand degrees of liquid metal. 3 of them were caught directly in it. All 3 were rushed to St. Catherine Hospital in East Chicago. It was already too late for most of them, and everyone on that floor that day likely knew it before the ambulance arrived. One of the 3 died 18 hours after the explosion. 18 hours is not a fast death. It's a slow one, and it means he was conscious for at least part of it, burned over 90% of his body, in an era when hospitals had none of the burn medicine they carry today. 2 more men died alongside him. A survivor, a man named George Smith, lived and never went back to work in a mill again. His body had already given everything it had left to give. That was a tapping side accident, not a charging machine cab. It matters to say that precisely, because precision is the only thing that makes a story like this worth telling, instead of just shocking you and moving on. But look at where it happened. Same open hearth floor, same furnace type this machine was built to feed, same total absence of anything between a man's skin and molten steel when the furnace decided, without warning, to let go of its contents in the wrong direction. The charging machine operator on that identical floor spent every shift with his cab pointed straight at the same kind of door, on the same kind of furnace, exposed to the same category of violence. Every single time that door swung open to take a load from his arm. There was no federal workplace safety agency to investigate what happened that day in 1948. None existed yet in this country, not for another 23 years. The only enforcement mechanism was whether a mill decided, on its own, that another funeral was worth avoiding. Eventually, mills did decide. The industry's own response tells you the rest of the story. Charging machines didn't get heat shields bolted onto their cabs because of a hunch. They got them because flare-back and molten metal violence kept finding the men closest to these furnaces, in whatever seat they happened to be sitting in, and somebody with a budget finally decided a sheet of steel welded to the front of a cab was cheaper than another burn ward and another funeral. That's the debt from Chapter 1, paid in full. This machine's territory, the floor it ran on, the doors it fed, the fire it was built specifically to keep men out of, burned people. Sometimes it burned the man in the cab. Sometimes it burned the crew working 2 furnaces down, doing maintenance the machine had no part in. The fire never checked a job title before it decided who to take. There's a harder question sitting underneath all of this, and it's worth asking plainly, instead of rushing past it. A machine engineered specifically to pull men back from a furnace ended up requiring a man to sit closer to that furnace than almost anyone else on the floor, for longer, more repeatedly, than the crew it had replaced. Is that a design failure in the ordinary sense? Not really. Nobody built the arm wrong or picked the wrong steel. It's a design that solved one problem completely and quietly created a smaller, more concentrated version of the same problem, wearing a different uniform, sitting in a seat that hadn't existed before the machine did. Regulators and unions spent decades chasing that gap closed, shield by shield, procedure by procedure. They mostly succeeded. Mills learned to purge a furnace properly before a door opened. Crews learned to read the sound of a heat the way a sailor reads weather, and pulled back from doors at the first sign something was building wrong. The job never became safe. Not by any standard you'd accept for yourself, but it became survivable in a way it hadn't been in Samuel Wellman's own lifetime. They were still closing that gap, mill by mill, when a much bigger threat arrived, one that didn't care about shields, procedures, or the decades of hard-won safety improvements bolted onto these machines one funeral at a time. It simply made the entire furnace this machine served obsolete, and it did it faster than anyone in this industry thought possible. Chapter 6. Cut rails, cold steel, and the floor that went silent. Remember that number from Chapter 3, 8 hours, sometimes 12, to run one heat of steel through an open hearth. Hold on to it, because here's the number that ended this machine's entire existence. 39 minutes. That's how long it took a basic oxygen furnace, a squat, tilting vessel with no arm, no rail, no charging machine at all, to turn a heat of steel roughly the size an open hearth would need 8 hours or more to produce. Engineers in Austria developed the process in the early 1950s, blowing pure oxygen straight into a bath of molten pig iron and scrap to burn out impurities in a fraction of the time regeneration ever managed. Canadian and American steelmakers were testing it within a couple of years, and by the 1960s, it was spreading through the industry like a verdict. The basic oxygen process didn't outcompete the open hearth. It humiliated it. A shop that used to run 1 heat per shift on a good day could now run a dozen. And it didn't need a machine built to reach into a furnace door and dump half-ton boxes of scrap, because it didn't charge that way at all. It tilted its vessel, poured the metal in directly, and let an oxygen lance do the rest. Electric arc furnaces, growing alongside it, did their own charging with an overhead crane and a bucket dropped straight through the roof. No rails required for either one. Here is the part that made this machine's fall total instead of gradual. Speed was only half the problem. Outside the one furnace design it was built to serve, this machine had no use at all. None. When the open hearth died in a given mill, the charging machine didn't get reassigned to a newer furnace down the line. There was no job for it anywhere else in the building. Every single one of these machines, in every mill that modernized, became scrap the moment its furnace went cold, because nothing else in the plant had a use for an arm built to reach through a door that no longer existed anywhere on the property. The open hearth had owned this industry completely before that happened. In 1955, 90% of all steel made in the United States came out of a furnace exactly like the ones this machine fed. 15 years after that peak, the collapse was already visible on the ground, and it kept accelerating from there. On February 25, 1971, U.S. Steel shut down the open hearths at its Lorain, Ohio works, a plant running roughly 7,400 production workers at the time, and replaced them with an $80 million basic oxygen complex that could match the old tonnage without a single charging machine anywhere in the building. 2 years later, Gary Works, home to an open hearth building 1,700 feet long, one of the largest ever built anywhere on Earth, began phasing its furnaces out entirely under pressure from clean air enforcement and daily fines that made the old equipment a liability instead of an asset. That pressure wasn't bureaucratic overreach. Open hearth shops like this one had spent decades pouring smoke and fine ash out over the towns built around them. Residents in mill towns downwind of shops like this one grew up calling the orange grit that settled on their porches after dark a nickname instead of a warning, because it fell often enough to need one. The same furnace that could take a man's skin in one violent second was, on an ordinary day, quietly doing the same thing to an entire neighborhood's lungs, one shift at a time, for decades, before anyone with regulatory power made it stop. By 1980, more than 10,000 workers at that one plant alone had been permanently laid off, with thousands more scheduled to follow. On September 19, 1977, a date steelworkers in Ohio's Mahoning Valley still call Black Monday, Youngstown Sheet and Tube announced it was closing its Campbell Works outright. Nearly 5,000 jobs were terminated in a single stroke, in a mill whose open hearth equipment was, by the company's own internal admission, 20 to 40 years behind current technology. Third-generation steelworkers walked out the gate that week having already known, in their bones, that it was coming. What do you do with a town that built its schools, its churches, its entire tax base around wages a furnace floor paid? You watch it happen, because there's nothing left in the building worth keeping the lights on for. Zoom out from any one plant, and the number gets almost too large to hold on to. American steel employment had peaked around 1953 at roughly 650,000 workers nationwide. Men whose wages built houses, sent kids to college, kept 1,000 small towns solvent. Between 1976 and 1986 alone, nearly 300,000 of those jobs vanished. A single decade cutting the workforce nearly in half. That wasn't the charging machine losing a job. That was an entire American way of making a living getting cut off at the knees, furnace line by furnace line, and the open hearth's collapse was the opening act of it. The first and clearest sign that the ground under this whole industry had already shifted. By the early 1990s, this country had exactly one open hearth shop still running, Geneva Steel, out in Provo, Utah, a plant that had itself been built almost overnight. 10,000 construction workers racing a war production board deadline in 1943 and 1944 to get its first blast furnace and its first open hearth charged and tapped within a single year. In December 1991, Geneva shut its last open hearth down for good. An era that began with the country's desperate wartime need for steel ended, almost fittingly, with the country's total lack of any further need for the machine that used to feed it. Geneva itself didn't last much longer. The company went bankrupt in 2002. The mill was dismantled in 2004, its casting and rolling equipment sold off piece by piece to steelmakers overseas. Its open hearth shop, left standing untouched for reasons nobody ever fully explained, as if the company itself couldn't quite bring itself to tear it down, finally demolished along with everything else. A photographer spent that year documenting the wreckage, piece by piece, so that at least the record of what it looked like coming apart wouldn't disappear with the steel. It wasn't only an American story. The same fall played out on every continent that had ever built one of these furnaces. East Germany's last open hearth went cold in 1993. Romania's last major open hearth shop shut down in 1999 and was scrapped over the following 2 years, though its smokestacks stood empty for another decade before anyone finally pulled them down too. Russia didn't retire its last one until 2018, and even then talked about saving it as a museum piece instead of cutting it apart. The machine, and the furnace it served, died everywhere it had ever lived, on a timeline that only varied by a few decades from country to country. Pittsburgh, the city that had built its entire identity around this industry, lost roughly 95,000 manufacturing jobs between 1980 and 1983 alone, 3 years. Homestead, Duquesne, whole valleys that had organized themselves for a century around the sound of a furnace charge going in, went quiet enough, within a single decade, that you could stand in the middle of what used to be a mill yard and hear birds. Most of these machines went the same way everywhere, cut apart with torches on the same floor they used to rule, hauled out as scrap steel through the same gates their own product used to leave through, fed at last into a furnace that wasn't theirs. Some charging floors were simply abandoned where they stood, left to rust inside buildings too expensive to demolish and too obsolete to reuse, rails buckling under their own weight, cabs stripped of glass, arms frozen at whatever angle they happened to be pointing the day the last heat was tapped. Rain got into cabs that used to be too hot to touch. Weeds came up through charging floors that used to be swept clean between every heat, because a stray scrap of wood or a puddle of moisture near an open furnace door was never a small risk on this floor. A few survived. At what used to be Bethlehem Steel in Pennsylvania, once one of the largest steel-making complexes on Earth, now mostly demolished, its blast furnaces left standing as the centerpiece of a public arts campus where concerts happen under structures that used to breathe fire. One Wellman charging machine still sits inside what was once the #1 open hearth. It ran there for decades, feeding furnace after furnace, then outlived its own furnace entirely when that part of the building was converted to newer electric furnace technology built up around it. Someone painted stars onto its steel body during the Cold War, and the stars are still there. It doesn't move anymore. Nothing feeds through its arm. It sits on rails that no longer lead to an open door. Samuel Wellman built the machine to keep a man's whole body out of the fire, and instead handed one man the seat closest to it. He also, without meaning to, built the one artifact that would outlast every furnace it ever fed, because a dead machine, unlike a dead man, can sit quietly for the rest of its existence and let people walk past it without ever asking what it cost. Walk through what's left of one of these shops today, in the handful of places where the walls are still standing, and the fire is the first thing you notice by its absence. No roar, no orange light bouncing off the ceiling trusses, just cold brick, cold rail, and a machine parked at whatever angle its last operator left it, its arm reaching toward a door that hasn't opened in 30 or 40 years. The stillness is its own kind of evidence. A floor this loud, this violent, for this long, doesn't go quiet by accident. Something had to beat it, and something did. Weigh the two sides of this machine honestly, and they don't balance. What it helped build was real. Steel that became ships, rails, buildings, the ordinary architecture of a whole country's growth. What it cost was also real. Men with 90% of their skin gone, towns that lost their whole economy in a single announcement, 300,000 paychecks erased in one decade. A machine doesn't get to keep the credit and dodge the bill. It got neither, in the end. It got cut into pieces and sold by the pound, on the same floor where it once decided, several times a minute, how close a man had to sit to the fire to keep this country in steel. They don't build a floor that hot anymore, at least not one that needs a man sitting 18 inches from the door to find out whether it will hold. That's not progress being generous. That's just what happens after enough men pay to find out the hard way.